Okay, today we're going to be looking at refraction. So refraction is again one of these fundamental properties of waves. And it involves what we think of the bending of the wave as it goes from one medium to another. And we can see that if you have a glass of water and you put a pencil or a straw in, it looks like it's been bent. And this is to do with what happens when the wave hits the boundary between two surfaces. Now here we've actually got three surfaces. You've got three mediums which the light is travelling through. You've got the air, you've got the water, but you've also got the glass here. And all these are going to have effect on the way in which the light interacts and changes. So what happens is when a wave crosses a boundary between two mediums, a few things happen. There's a change in velocity. There's also a change in wavelength. But this is important. There's no change in the frequency. So if we let's say this is a block, a prism, and this is our normal to the prism, and the light comes in at this angle, this angle here. We'll call this θ1. Then this is air. Say this is glass. Glass has a higher density than air. So when it goes from when the wave goes from a low density to a high density medium, it bends towards the normal. So from low density to higher density, θ1 is going to be greater than θ2, and the velocity is greater in the low density medium. Now there's a relationship that to determine the angles involved here, and it's called Snell's law. And it says N1, which we'll define N in a minute, N1 is the refractive index. Sine θ1 is equal to N2 sine θ2, where N is the refractive index and θ1 is the angle of incidence, and N2 is the refractive index of this medium. Let's get rid of that there. And θ2 is the angle of refraction. Not made that very clear at all. So how do we define N? So N, actually we'll get a new page up. Or we'll get rid of this. So N, the refractive index, is a ratio of the velocities. So N is going to be the speed of light, if we're thinking about light waves, the speed of light in a vacuum divided by the speed of light in that medium. So this is the speed of light in a vacuum, and this is the speed of light in a medium. Now, for our purposes, we're going to consider the refractive index of air to be 1. It's a wee bit higher than 1 because air is obviously more dense than a vacuum. But for the purposes that we're going to be doing, the calculations will be accurate enough to consider the refractive index in air to be equal to 1. And yeah. So let's do an example of using this. Let's get rid of that. Can't find that. There we go. So we've got this set up here, and we've got air, and we've got perspex. And here's our normal. Here is our light coming in here, and it's coming in at 30 degrees, and its angle of refraction is 19.6 degrees. What is the refractive index of perspex? So n1 sine theta 1 equals n2 sine theta 2. n1 is 1 times sine theta 30, because remember air's got a refractive index of 1, times n2, which is what we want, times sine 19.6. So n will be sine 30 over sine 19.6, which gives us 1.49. Now, the more dense as a medium, the higher the refractive index of that medium will be. Now, what happens if our wave, here's our normal, and we get a different colour so it'll show up as being different. What happens if our wave comes in parallel to the normal? So our wave hits the medium at the perpendicular. Well, no refraction will take place in that instance. So no refraction occurs if the wave hits the medium boundary at the normal. Now, let's get rid of this page and let's consider our wave equation. V equals F lambda, and we've said that at the boundary, the frequency remains constant, and there's some quite complex physics involved in that to understand why the frequency would remain constant, and it's to do with the electromagnetic fields of light and how they interact at the boundary. So let's think about, if we rearrange this, we get F equals V over lambda. So the frequency, so let's get our So here's our N1, our N2, theta 1, theta 2. So V1 over lambda 1 must equal V2 over lambda 2. So if the speed decreases, lambda must increase. So if we think N1 sine theta 1 equals N2 sine theta 2, then the ratio N2 over N1 must equal the ratio of, so N2 over N1 must equal sine theta 1 over sine theta 2 by rearranging this. Which means our ratios of wavelength must be the same as this, and the ratio of the two wavelengths and the two velocities must all be the same. Now what also, so yeah, let's do an example with a wee bit more difficult example, and then we'll talk more about wavelengths and refractive indexes. So let's get a prism here. Now remember, we've got with this, we need to think about the normal to the surface boundary. So the normal to the surface boundary is going to be here, and that's normal to here. And our wave is coming in this direction at 30 degrees. And this is air, and this is some medium, maybe glass or something, with a refractive index of 1.2. And it's an equilateral triangle. There we go. So this comes in, and then, it's refracted by some angle A. But then here, it's going to, the angle of refraction is now going to become an angle of incidence, B. But because this is going from a high density to a low density, the angle of refraction this time is going to be greater than B, and it'll be 44.0 degrees, because it's going back into air. So let's want to calculate the missing angles. So we know of Snell's law. So the N1 is just 1, the refractive index of air is just 1, so we've got sine 30 is going to be equal to 1.2 sine of angle A. So the sine of angle A will be equal to sine of 30 divided by 1.2, working all that out, A will be 24.6 degrees. Now, here we want to work out angle B. Now we've got the sine of the end. Just write Snell's law again. So this is now 1.2, and this is now sine B, and that's now 1, and this is sine 44. So sine of B is going to be the sine of 44 degrees divided by 1.2, giving us an angle for B of 35.4 degrees. Now, the refractive index is dependent on the medium, i.e. the density of that medium, but also the wavelength of the light, of the wave, because this works for other waves, not just light. So as a general rule, the longer the wavelength, the lower the refractive index, and this results in the change of refractive index is the reason for prisms splitting light. So red has the longest wavelength of visible light, so the refractive index is less for red light than violet. And if you think about Snell's law, if this is the angle of refraction will be therefore different depending on the wavelength of the light. This is also why we get rainbows and why we get beautiful patterns from water droplets in the upper atmosphere causing things like halos, and if in the very cold you'll see beautiful kind of iridescent rainbow features caused by the light being refracted through ice crystals in the upper atmosphere. Now it's also similar to the effect we saw with diffraction gratings, but it's important to understand the differences. So the differences between making spectra with diffraction gratings versus prisms. So firstly, gratings rely on diffraction and interference patterns, whereas prisms rely on refraction. So you're making these three properties of waves, diffraction, interference and refraction, are being used in different situations, all to create the same effect of showing the spectrum of light of the original wavelength. But it's important to know that that what's actually causing the spectrum are these three different principles working in different situations. So with the grating it's diffraction and interference, and with prisms it is refraction. So prisms tend to produce a single spectrum from a single ray of light, but gratings produce a number of spectra by the interference pattern of maxima and minima. And finally, the order of the colours by a prism are in reverse to that of a grating. So the deviation from the central line is least for red. So in the prism you've got, you're going to have your, let's get a bit of red, trying to get a red colour. So you'll have your red nearest the normal, and then it will go to your yellows, and then your blues, and your purples. Whereas if you were to see in a refraction grating, it would be the opposite way round. So I hope that helps.